Okay, in today's lecture, we're going to talk about percentages and density. And we're going to use these as part of our dimensional analysis toolkit that we learned about in the previous lectures on the metric system and dimensional analysis. So if you didn't watch those yet, please go back and watch those and learn about the metric system, its history, unit factors, and dimensional analysis. Okay, but today we're going to talk about percentages and density and use them in our dimensional analysis. So let's start with percentages. And with any topic, it's really important to just lay the foundation and the groundwork of how do you define this topic. And a lot of science is about knowing the vocabulary and what it means. So it's important not to just gloss over things, but let's define concretely here, what is a percentage? Okay, a percent is a ratio of parts per 100, right? Many of us know that, we're familiar with it. But just to spell it out quantitatively, a percentage is one quantity over total sample multiplied by 100, right? And that's what gives us our percentage. You can say the percent doesn't have to be there, but that's what gives us our percentage. These are used quite often in chemistry. Sometimes you'll see this as a mass percent. Sometimes you'll see this as a volume percent. You could even talk about this if you wanted in a mole percent, but we haven't quite got to the concept of a mole in this class. And so in each of those cases, it's about specifying sort of one element in particular usually, or one compound that is part of a more complex mixture of elements or compounds. So we usually specify the percent of a certain element in a total substance. So you might say this substance we're trying to identify, we do some fancy experiments, and we figure out it's 42% copper and 58% tin. And maybe that is some alloyed material, for example. So let's look at how you might actually use this to solve some problems in chemistry. So if you have a sterling silver necklace, so maybe you get a necklace from your companion, and it's made out of sterling silver, and your intuition is, oh, is that pure silver? That must have cost a fortune. Well, it probably did cost some money, but it's actually an alloy of silver and copper. That's what makes it sterling silver. So this sterling silver chain contains 18.5 grams of silver and 1.5 grams of copper. So it still is mostly silver. But let's quantify exactly what is the mass percent of silver in the chain. And so we're just going to literally plug this into the formula we just talked about. And maybe inherently you know how to do this, but let's slow down and actually look at what is the percent of silver. According to our formula, it's the mass of that one thing, right, which is going to be 18.5 grams of silver, divided by a total mass, okay? And the total mass is all the things in the sterling silver. So both of these elements we have to concern ourselves with. If there was 3 or 4 elements, we'd have to add them all up. But there's only 2 elements here we care about in the total amount. So it's 18.5 grams of silver plus our 1.5 gram of copper. And then we have times 100. And so you can do all that on your calculator, and I don't have a calculator in front of me, but I think this is something like 92.5%. Okay, and I'm going to use 3 sig figs here for various reasons of significant figures. The numerator is 3, the denominator is an addition, and you always keep out to the 10th place if they both go to the 10ths. Then this becomes 20.0, which is 3 sig figs, and then 3 sig figs over 3 sig figs gives us 3 significant figures. So that's why we're going out to 92.5% and not rounding to 93. Okay, so that's percentages. You will also not only have to calculate them like this, but use these percentages as a unit factor. And again, last lecture, we really talked about using the unit factors as dimensional analysis calculations. So here you might actually be given a percentage in a problem. So yes, you might be asked to calculate a percentage. You do it just the way I just showed you, right? But if you're given a percentage, realize that you can use this as a unit factor. Okay, and this question is pretty straightforward. You might be able to figure it out without going through all the trouble of dimensional analysis, but I guarantee you there can be problems much harder than this, and it really helps to write out your units and approach it as dimensional analysis. Just take that from me, 30 years of chemistry experience here. I guarantee you're going to make many less mistakes if you actually write out all your units and do the full dimensional analysis. So these percentages can be expressed as these unit factors, right? So 25% could be 25 of, whatever the component is, component A, out of 100 total. And so just keep in mind that you want to make these sort of ratios as part of our dimensional analysis. So let's look at this. The moon is 4.7% iron. How many grams of iron are in a 92-gram moon rock? So let's think back to our previous dimensional analysis approach, the 3-step method, Prof. Melko patented method of success in dimensional analysis. How many grams of iron? So whatever it's asking for, that goes over here on the right. Grams of iron. Okay. On the left is the given information. And you're given 2 bits of information here, 92 grams and 4.7%. But now you remember from Prof. Melko's lecture that these percentages might be the unit factor. So let's start off with the 92 grams total. And then we can think about, well, how am I going to get from grams total to grams of iron? And that's where you can use this percentage as a unit factor. Now, we learned last time that whatever unit is written here immediately goes in the denominator of my unit factor. So whatever unit is there goes down here. So I'm just going to write grams of total. And we also learned that if it's a one-step problem, which this will turn out to be, whatever unit is here can go right here in the numerator. Because just like numbers, a unit, grams total, divided by itself, grams total, goes away and cancels, right? And this unit is what we want to be left with. So now let's think about this 4.7% iron. That is that amount of iron over a total. And look, we have iron over a total. So what we're going to do here is put the 4.7 and the 100 here. And this is what allows us to calculate, multiply across the top, divide by the bottom. We should get 4.3 grams as our final answer, multiplying across like this, 92 times 4.7 divided by 100. So that is a little bit long-winded in terms of a dimensional analysis approach to percentages, but it is the one that will always lead you to the right path. Because you could have been asked it a different way. You could have been asked, if there are 4.3 grams of iron in this moon rock, right? What is the mass of the moon rock if it's 4.7% iron? So it could have been asked the other way, where you were given 4.3 and had to solve to get 92, and then the unit factor would have been flipped. But as long as you follow the units, always let those drive the bus of dimensional analysis, you'll do just fine. So that's percentages. One of the things in chemistry you'll come across that is used in these unit conversions. Volume is another sometimes tricky type of unit conversion problem. Again, it's all about those units. Keep track of the units and you'll be fine. Volume is expressed in different types of units. Of course, we know that volume can be expressed in something like liters, right, or milliliters. And we saw that in the previous lectures of the metric system. But some things it's pretty easy to just hold a ruler up to, and so you can measure the centimeter length, the centimeter width, and the centimeter thickness and get a unit like centimeters cubed, right? Because each of these should be in the same unit. Maybe it's centimeters here. And just like numbers, if it was 2 times 2 times 2, that would be 2 cubed. Well, the unit's cube as well, so it's centimeters cubed. So keep in mind to cube your units if you're calculating a volume. If the block below, I guess that's where I'm supposed to draw the block because I've eliminated the figure for copyright purposes, but here's my block, and it measures 2 by 3 by 1. So clearly this dimension is the 1, we'll say this dimension is the 2, and we'll say this dimension is the 3 centimeters. The volume then is length times width times height, and that's how we get our 6 cubic centimeters. Now, what can be more difficult is, say, change this into a different type of unit. One thing I will say and note here is that 1 cubic centimeter is equal to 1 milliliter. So if you ever want to change cubic centimeters to milliliters, that's easy. No maths involved. You just change the unit. Why? Because a cubic centimeter is a milliliter. And it's not a coincidence. If you go back and watch our lecture on the metric system, you'll see that the way we defined a meter and the way we defined a liter is such that they're related to one another. But let's try a conversion problem. 498 cubic centimeters converted to cubic inches. So you can feel free to pause the video here and try yourself. Otherwise, I'm going to just go forward and solve it. So according to the method that I have patented, trademarked, etc., what is the volume in cubic inches? So that's what we want, inches cubed. The information I'm given is 498 cubic centimeters. What is the volume in cubic inches? So I know whatever unit is right here, I'm going to write it down here. Okay, but I'm going to take a brief aside here, right? And I'm going to encourage you, if you're not used to cubic units, to think about writing this out as 3 of them, okay? So and think of it not as a cubic unit, but 498 centimeters times centimeters times centimeters. There's 3 of those centimeters involved in a cubic centimeter. And when you write it like this, then it's quite obvious that you can put one of these centimeters down here because you know from this unit equation, you can get rid of one of them. 2.54 centimeters in 1.00 inches. And that's great. And I can't tell you how many students will just do this one conversion and think they're done because look, centimeters goes away. Centimeters goes away, but you're not canceling the cubic centimeter. You're canceling one of these 3 centimeters. So this necessitates that, well, you probably are going to need more unit factors here. And you're going to end up needing 3 unit factors to cancel out each of the 3 centimeters. So I'm just going to pay attention to the units, and I'm going to put 3 centimeters down here so that I can cancel each of these centimeters. And the numerator of each, well, I have to look at my unit factor that relates centimeters to something. And so the numerator is going to be 1.00 inches. And now look at what's convenient, right? The centimeters have all canceled with each of these 3 centimeters for cubic centimeters, but also this inch, and this inch all multiply together to create this cubic inch. So that's good. I just have to check here that the units should work out. And so 498 times 1 times 1 times 1 divided by 2.54 divided by 2.54 divided by 2.54 should give us something like 30.4 inches cubed. Three sig figs, since that was the number I was given here. And there's also 3 sig figs in each of these measurements. Okay, so 30.4 inches cubed should be our answer there. So that is volume conversions, that is percentage conversions. One more thing we have to get to, and that's density. And the way I like to introduce density is with the story of Archimedes. Now, volume, as we saw here, is easy to measure because you can easily hold a ruler up to this, brick, whatever this is, this solid block, is probably something you can easily access. But what if you have an object that is much more faceted, right? That is much harder to measure with a ruler. It has a lot of concave and convex shapes in it, and it's really hard to get a ruler into all the nooks and crannies. Well, there must be other ways to get a volume. And this leads us to volume by displacement, right? Many solids are not perfect, nicely ordered shapes. These volumes can be measured by measuring the amount of water the solid displaces. And this was first figured out by Archimedes, who was a scholar around 300 BC. He was born in Sicily, specifically a town called Syracuse, I believe, which at the time was really a hub of arts and science in Italy. And he grew up He went off to college at the most prestigious academic institution, Alexandria, studied there, came back to his birthplace of Syracuse, and at the time there was this king that ruled Syracuse, and this king, known as King Hiero, hired Archimedes as his scientist. Now, King Hiero was also quite wealthy and affluent, and decided that he wanted to fashion a big crown for himself. So that's what's shown here. And you can see this crown down here has a lot of edges to it, right? There's a lot of things that make it hard to measure with a ruler. Now, King Hiero commissioned this crown and gave his goldsmith this, I don't know, some mass, maybe 3 pounds of solid gold to make the crown out of. And the goldsmith took this 3 pounds of gold, went off, commissioned, made the crown, and returned it to the king. But there were whispers. And the whispers suggested that the goldsmith substituted some of this gold. So while it had some gold in it, right, he took a chunk out of it and kept it for his own profits and substituted in some other metal. So now instead of being 3 pounds of gold, well, maybe it was like 2.5 pounds of gold and a ½ pound of something else, maybe silver, something else cheaper. So that was sort of the hearsay. And the king, hearing this, thought, you know, that is highway robbery. I have to catch this goldsmith, but I don't know how. And so the story goes that Archimedes was tasked with this to discover how you could figure out whether a gold crown that weighed 3 pounds was actually completely gold. Now, Archimedes knew that something specific to each element is a density. Okay, gold, silver, you can have a 1 kilogram thing of silver, 1 kilogram thing of gold, right? Doesn't matter. You can have a 1 liter volume of gold, a 1 liter volume of silver, doesn't matter. But something specific to the element is its density, right? The density is unique to each element. So the density of gold is different than the density of silver. So if this crown is pure gold, it'll have a certain density. And if it's gold mixed with something else, it'll have a different density. And the density is expressed as mass over volume. So while you could easily weigh this crown out on a scale, it was very hard to measure the volume. And so this was Archimedes' problem, is he was trying to think, how can I measure the volume of this crown? Because it's really hard to get a ruler in all these places and just multiply length times width times height. And so he was off in the baths, as one was wont to do in those days. And as he relaxed down into the bathtub, he saw this water level rise higher and higher. And eventually water spilled out of the edge of the bath. And the story goes that he, at this very moment, realized this was how he could solve the king's problem. And apparently he shouted, "Eureka, Eureka!" and went running off down the streets, completely naked, screaming this all the way to the king's palace. And what he figured out was that as you put something down into a level of water, much like the bath, you could take this crown and put it down in here. The water level will rise, and eventually some might spill over the edges. The amount of water that is displaced here or moved is equal to the volume of, in this case, the crown. So this is known as volume by displacement, right? What you do is you partially fill a container with water, you measure that water, you add the solid and measure the new volume. And so the amount of volume that is changed here, a delta V, or a change in volume, is going to equal the volume of the solid. And so what he realized is he could do this with the crown. He could find the volume of the crown. He could plug it into this formula and calculate the density of the crown. And that's exactly what he did. And he found that the density of the crown did not equal the density of the gold, of pure gold. It was quite a bit less, meaning the goldsmith did try to rip off the king and substitute some of the gold with something cheaper like silver. And unfortunately for the goldsmith, Archimedes was brilliant enough to realize how to do this. He reported it to the king, and well, the goldsmith, let's just say things didn't quite work out for him. So that's volume by difference, and specifically density. Density is mass divided by volume. That's what we just talked about. Usually expressed in grams per milliliter. Or again, since milliliter is equivalent to cubic centimeter, you might have grams per cubic centimeter. Okay? You could have kilograms over liters or grams over liters. It just needs to be a unit of mass over a unit of volume. But these are the typical ones that are used. And importantly, I'll write it again because it's so important. Density is unique to an element. So gold has a certain density, carbon has a certain density in particular structures. Nitrogen will have a certain density, lead has a certain density, silver has a certain density. And it's all about the way that these atoms of that particular solid stack together in a crystal lattice. And we'll learn more about that at different times in this class. But for now, that's what you have to know about density. It is about how these atoms arrange themselves in a crystal structure. Most of the time, we're talking about a solid in the density, but you could have gas or liquid densities as well. Now, you can estimate density in the lab as well. Maybe you don't have a way of calculating mass and volume separately and dividing them out. Or maybe you just want to take a shortcut. So one of the things you can do is get a graduated cylinder. Pretend that's what I've drawn here. I'm not sure what I've drawn, but pretend that's a graduated cylinder. And maybe down here at the bottom, you put a liquid that is very dense. And on top of that liquid that is dense, you pour water. And on top of that water, you pour another liquid. And now you have 3 liquids of different density, right? The whole reason you'll see oil separating out on the top of water is because oil is less dense than water. But now you have these 3 liquids. And so now you can take something that you don't know the density of, and you can drop this solid inside here and see where it settles out. And if it floats on the top, well, it's has a density that is less than this top liquid density. And if it floats right here, then you've sort of bracketed that the density is greater. Let me write this out a little bit different. The density of that object is greater than this first liquid and less than the density of this second liquid. Right? And well, if the block instead settles out here, well, then it's a density less than the green and greater than the middle water in this case. And if it goes all the way to the bottom, well, then the density is greater than all of them. Okay, so if it sinks, it has a higher density than the liquid it's in. If it floats, the object has a lower density than the liquid it's in. And you can arrange this with many different layers if you want to really bracket down to an exact number, or a very precise number, I should say, what the density is. Or you could just divide mass by volume and calculate it that way. The last thing I want to discuss here is how you're going to use this density as a unit factor. So kind of like with percentages, you can use this as a unit factor. So it's important to keep in mind that when you read through a big, long math problem, okay, you might run across a percentage or a density. And I want you to have sort of these alarm bells going off that these could be my unit factor. It doesn't mean it's definitely going to be, but you want that to sort of trigger in your head that this could be a unit factor. And that's what we'll see in this problem. A car battery has a 1275 milliliter battery, 1275 milliliters of battery acid. If the density is 1.84 grams per milliliter, how many grams of acid are there? So again, it's shown on the screen, but grams of acid on the right given information on the left. You're given the density, but that density is going to be a unit factor, and it's just up to you to figure out how to organize it in here. Obviously, milliliter has to go on the bottom to cancel milliliters, and so grams goes on top, and 1.84 goes with grams, right? Because that is explicitly what's said. Also, as I said last time, a lot of times these compound units give students problems, so I like to write them instead like this. Whatever the second unit here is in the compound unit, it's always per one of those, right? So if it's 52 miles per hour, or we could say meters per second, that's the same as saying 52 meters over 1 second. And when you write it out like that, it's easier to see it as a unit factor that you can manipulate for the particular problem. So with that, that finishes this lecture on density and percentages and Archimedes' great tale of figuring out the king's crown. In the next lecture, we're going to talk a lot about temperature, energy, heat, specific heat, and the differences of all of these terms. So that'll do it for this lecture. See you next time.